everybody. This is KNES 415 Biomechanics. If you are in KNES 310 and you comment that you watched your lecture on this one, neither here nor there. So today we're going to apply one case. We'll do this every lecture, but we'll apply one case of open-closed chain, and then we'll get into new stuff, kinetics and kinematics. So remember, chains, you guys have heard of the kinetic chain. A lot of times they'll talk about in terms of throwing, the kinetic chain, and it implies movement patterns, movement strategies, and sometimes these patterns can have fixed distal segments or freely movable distal segments. So basically, remember in 310 we talked about the illusions. It looks like it's moving, but it's not. It looks like it's not moving, but it is. A lot of times it's kind of these switcheroos where, for example, let me pull up my examples that I have for you guys in class. So when we're talking about chains, we're not talking about different necessarily joint motions. Sometimes the joint motions are the exact same. What we are talking about is movement patterns where distal segments are either free to move about the proximal, or the proximal segments are free to move about the distal. Where's the third one? There we go. So what I'm going to do is I'm going to show you guys 3 examples. Okay. So the first one, we have the traditional pull-up. Now, this exercise or this movement pattern forces you to have simultaneous motion, elbows and shoulders. We could talk about scapula, but just elbows and shoulders for just the conversation. And then on top of it forcing you to have simultaneous motion, the distal segment, in this case your hands, because although your feet are moving, your feet aren't getting you up in the air over that bar. Does that make sense? The hands are transferring your muscle force in order to do the outcome of bringing your center of mass up and letting your center of mass down. That's where the magic is happening at the hands. Your hands are not allowed to move linearly nor angularly. That bar is preventing your hands from going up and down. The bar is preventing your hands from rotating around the side. So this would be an example of closed, closed. The hands are closed to linear and they are closed to angular. In fact, when you're on a bar, the closed to angular can be emphasized. That's why gymnasts use chalk, right, to help their grip, because they don't want their hands to move angularly. They don't want their hands to slide on the bar. Think about if you're doing a bench press and you grab a brand new bar and they have those ridges, those little bumps, those little knobs, imperfections, those little spikes. That's to help prevent your bars from sliding, because you want to close those angular roads. That's all that is, guys. It's to help prevent you from sliding, thus closing a road that's different from up and down. Okay? Now let's go to this exercise. Okay, a lat pull-down. Similar, same motions, elbows and shoulders, right? But now the hands, the distal segments that are responsible for transferring that force, the hands are free to go linearly up and down. Now you can't independently go angular with the elbows. In other words, I can't be doing a lat pull down and say, hey, elbows, why don't you just extend independently from the shoulders? You can't do that because the bar is preventing. You'd have to snap the bar in half, right? But take a look at this exercise. Lat pull down, but a single arm. So this would be an example of a more open exercise where you can kind of move the right arm independently of the left. And you could technically, now this is really tough to do open, because you're pulling the handle down. And so just elbow motion is going to be very tough to do that. But the point is that this is a heck of a lot more open than this. At least I can move my right arm at a different speed than my left. In other words, I can do this exercise faster with my right than my left. This one, you have to move your arms at the same speed. So again, there's pros and cons to each. Okay, we'll work through, I'll try to have a different example. So for you guys as we move forward, okay? Now we're gonna get to some meat and potatoes of biomechanics and physics. So this is on page roughly, let's see, 18-ish, but it's the kinetics and kinematics. This is the meat and potatoes of biomechanics. Biomechanics, in essence, is just applying two different areas of study or application of knowledge. It's all in how you want to look at it. And oh, by the way, the secret word. Hello, secret camera. The secret word of the day to confirm that you guys watched this video is the word finished. In the comments, write the word finished. And listen, I don't want to hear, I'm making this easy already. I'm giving you points for just watching. I want to hear, well, every time you mention a secret word, I'm in the bathroom. Just pause the video, man. Pause the video and go let the dog out. Pause the video, go to the bathroom, come back, press play. No, excuse me. Finished. That's the code word for you to confirm that you watched the video. In the comments, you write finished. All right. Two areas in biomechanics, and everything ultimately comes back to these two areas. And that is the concept of cause and effect. The cause, in this analogy of cause and effect, something you guys are familiar with, is forces. And in biomechanics, forces are categorized by a term called kinetics. Kinetics is forces. Kinetic chain, that's force chain technically. A lot of times they talk about the kinetic chain and they move. Kinetics is just motion variables. Now, there's a lot of different things in motion variables, and I'm going to get into some specifics in the next lecture. Anything, I'm sorry, 4:30 in the morning. There's a lot of variables with forces of kinetics because there's a lot of different types of forces. We're going to get into movement variables and different movement terms, but this is dealing with forces first, kinetics, causes. So think about in high school physics, college physics, an object at rest stays at rest, object in motion stays in motion, unless what? Unless there's something responsible for it changing, right? And that's what a force is. A force is a catch-all term. A force is a general term because there's a lot of different types of forces. Defining force, the easiest way to define it without using an example, because we can't technically define things with examples, that doesn't do us any good, is the definition of force is an influence that is trying to change the motion of another object. So the influence can come from object one, but that influence is trying to change the motion of object two. See what I'm trying to say? And it's really kind of weird. Objects can't change their own motion. It's kind of a weird truth. This ball is an object. This ball can produce an influence on other objects. Like if the ball slams into the ground can feel a force from the ball, but the ball cannot feel a force from the ball. The ball can feel a force from another ball, and this ball can give that other ball a force, but this ball cannot give itself a force. This ball cannot give itself an influence. And if you're like, well, what about gravity? Not on the ball. The ball feels gravity from planet Earth. Now, the ball does have gravity, but the ball doesn't feel its own gravity. Planet Earth can feel the ball's gravity insignificantly, but the point is that this ball cannot apply a force to itself. So if the ball cannot apply a force to itself to influence its own motion, and the ball is an object made up of stuff, guess who else cannot apply a force to itself? You. Now, when I say apply a force to itself, you're like, I can do it. You can't apply an accelerated force, in other words, an unbalanced force, a force that would change your motion, your whole body's motion. I'm not talking about your neck. I'm not talking about your elbow. My point is that you cannot produce a force on yourself to make you move. What? I move all the time. I go around the house and I go exercise. And notice when you do all those things, you're not floating around the house. You're walking on the ground, and it's actually the ground that's moving you. You push on the ground. Think about it. If you want to walk this way, you push on the ground that way. And when you push on the ground that way, the ground then in turn pushes back on you in the direction you want to go. It's actually the ground that's moving you. You're trying to move the ground, but the ground isn't going anywhere most of the time. I mean, think about it. If you were going to jump as high as you can, and you jumped as high as you could on cement, you're going to jump higher than if you jumped as high as you can in sand. Like if you're playing sand volleyball, it's the same muscles, it's the same you, it's the same stuff. Well, why do you get higher because this proves that you don't move yourself. The ground moves you for the most part. You're pushing down on the ground, and in sand, you actually move the sand. You actually influence the sand to go down. Well, guess what? That sand doesn't push back on you as much when it's actually moving down. Versus jumping on cement. You try to move the cement ain't going anywhere. You get all of that force back. So indirectly it's through you. But if my feet are off the ground, like if I'm laying down on the ground and I'm trying to do the same motions, right? I'm laying on a table and I'm extending my hips and extending my knees, I ain't going anywhere. Same me, same muscles, same motions. But I don't move myself. And that's kind of important because if you accept and realize that, then you can start looking at things a little differently. Heck, you athletic trainers out there, you guys know darn well, one of the first things we do when we're at a game is we observe things that could be potentially dangerous, hazardous. We look for potholes and we look for dangerous situations. Why? Because environment matters. Environment matters. That's actually what's going to be imparting force back at me to influence my motion. Hey, what's up, little girl? Little baby girl. You trying to go outside? Be right back. Come on, buddy. Come on. Come on. Come on. No, don't go over there. Come here. Come here. Come here, little baby girl. Oh, okay. Sorry. Okay. So, kinetics forces. There's a lot of different types of forces. For this class, we are only gonna, I'm gonna only hold you accountable to ones that are significant to human motion. So in other words, electromagnetism is a force. There's four like universal forces, you know, like gravity is a force, electromagnetism, the strong and the weak nuclear force. We don't really apply strong and weak nuclear cell forces, right? That's like for nuclear engineers, people that are making nuclear power plants, people studying the sun. Not this guy, right? Electromagnetism, how often remember in 310 we said an external force is trying to move you? How often was a magnet trying to move you. Like you'd have to put something metal, and then you'd have to have a magnet. Rare, never happens. Not saying it can't happen, but it rarely happens, so we're not going to worry about that. Gravity. Gravity, the attractive influence or force of objects that have mass. So gravity, the force, the influence of gravity of planet Earth, that's very important to remember, that the ground itself isn't pulling down on me. And how do I know that? How do I know that the floor right here isn't pulling down on me? I mean, heck, if I drop the ball falls to the floor, and it's the floor that stops the ball from falling down. But how do I know that it's not that actual wooden floor in my house that's pulling down on the ball? Because I can do an easy thought experiment. I can imagine digging a hole a mile down, like let's pretend I was magic. Hole. And I drop the ball. Is it going to stop at the floor? Of course not. It's going to keep going down the hole. Because it's not the floor that's pulling down on the ball. It's literally the center of planet Earth. 3,000 plus miles down. The center of this planet. So when we talk about gravity, we infer, we assume, but the reality is that it's the planet. It's planet Earth. So if you think about it, if you're right here, oh, Mama Kitty, you too? Okay, come on. Nope. Sorry, guys. Let's say this is planet Earth, and let's say you are here. You have everything on the other side that's pulling you. Just think about how big Earth is, man. Earth is big. Think about how much stuff is in just one skyscraper. How much stuff is in one building. You have the entire planet. And the crust, right? The outer layer, the little skin, dude, that's where the heavy stuff, the real significant heavy stuff is all the way at the bottom. And you think about if you take a glass of a clear glass, right, where you could see through, and you take some pond water or some river water, and you just let it settle. The heavy stuff settles at the bottom. Same thing with planet Earth. The heavy stuff, the nickel and the iron, is all coalesced towards the center. This is kind of a cool fact. Our planet is so big relative to us, right? So you think about our atmosphere, right? Miles and miles of air. It's a big atmosphere. Well, to us, it's big. But if the Earth was scaled down to the size of an apple, the atmosphere wouldn't even be as thick as the skin of that apple. That's the light stuff. The heavy stuff is in the middle. So the majority of Earth's stuff is in the core, in the middle. And that's pulling down on us. It's trying to come here. So the center of the planet is pulling down on us, but the surface of the Earth is preventing that from continuing. It's preventing us from going down there. So gravity is really important for us. It's a force that influences our motion a lot. We did a ton of this in 310, right? What motion is gravity trying to cause? What motion is gravity trying to cause? What motion is gravity trying to cause? And we can get gravity to work for us, like with machines, right? So in other words, we can have an exercise that might be, watch this, so push down. I'm gonna pull up this exercise, tricep push down. Tricep push down, okay? So watch how gravity, we can trick gravity, we can redirect it, okay? So look at this exercise right here. And the cable is trying to pull my hands up, right? It's trying to flex me. But the reason the cable is trying to pull my hands up is because I imparted a pulley on it. And pulleys are little mechanical tricks. We're going to talk about that down the road. But the weight stack, you see the weight stack right there? The weight stack still has gravity trying to pull down on the weight stack. And because of leverage, we're going to talk about how first-class levers redirect applied forces. The weight stack pulls down because of gravity, The weight stack pulls down because of gravity, and the pulley redirects that force by pulling up on the cable. Gravity pulls down there, redirects that force to pull up on the cable. But it still comes down to planet Earth. Who are you truly playing tug of war against in that exercise? This is cool, man. This is really cool. Who are you really playing tug of war against? It's not the weight stack. It's planet Earth. It's you versus planet Earth. The mass, the gravity generated by the mass of planet Earth against your muscles. And who represents your muscles in that exercise? Your hands. Your hands are the voice of your muscles. So that's kind of cool. Next time you're working out, think about it. It's you versus Earth when there's gravity involved. Okay? So gravity is an important force for us to not. We don't have to understand how it works. Newton had no clue how it works. Newton just knew how it worked. Newton understood that the moon is free falling to the earth, just like an apple would free fall to the earth. Now, if you say, well, Campbell, if the moon is free falling to the earth, why doesn't it ever hit the earth? Well, that's because the moon, in addition to free falling to the earth, it has sideways motion. So it's, as it falls to the earth, it falls to the side and it misses. It keeps missing the earth, and that's what we call an orbit. And Newton had a really cool, in his book Principia, he had a really, really cool example of how this works. So imagine this is an earth, right? This baseball represents the earth. And imagine there was a cannon at the top. And he actually drew it. He drew, let's see if I could draw this for you guys with my little piece of paper here. This is a cool story. I think you would dig it. So in his book, he drew this little earth, and then he had a little cannon, and then I'm going to explain. So he drew this little earth, and then he had this cannon, and he said, now imagine that cannon would shoot a cannonball with a certain velocity. And of course, the cannonball would fall to the earth. It would make a parabolic curve. It would be traveling across with some across velocity, across speed, and it would curve down to the earth. Now, if it didn't get shot with across speed, it would just fall to the earth, right? But because it has some across speed, it's going to go across and down. It's going to have this little parabolic curve. And he said, now imagine shooting the cannon a little faster. It would cover more distance, right? You see how it'd go further. He's like, now imagine shooting the cannon even faster. It would curve even more. Now imagine shooting the cannonball with enough speed that it would curve around the earth as it fell down and literally keep missing it. It'd come all the way back and knock you upside the head on the other side. This dude figured that out. That the earth is free falling around the sun. That's what the gravity, the mass of the sun is pulling on the earth to go meet it. The problem is that the earth has a ton of sideways velocity. So as it free falls to the sun, it keeps missing. The moon is free falling to the earth, but it has so much across speed it misses. So next time you think about astronauts in orbit, just remember they are zooming around the earth with a ton of speed, and they are free falling to the earth, but they just keep missing. While we're on the concept of gravity, a couple, hopefully you find this interesting, but some people will say, well, there's no gravity in space. Yes, there is. How can there not be? The Earth is pulling on the moon. What you think's in between the Earth and the moon? Space. And the moon pulls back on the Earth. So the trick there is that when you are free fall, you are weightless. When you are in free fall, you're weightless. You can do an experiment where you take a cup and you poke holes in the cup, and if you fill the cup with water, the water is going to leak out the holes, and the water at the bottom hole is going to be shooting further than the ones at the top because there's more push from the top. But when you drop the cup, it stops, the water stops to shoot out because it's weightless as it free falls. And then once it hits the ground again, the water pulls out. The point is that when you see astronauts free floating and the ball is floating, there's still gravity. It's just that the ball, the astronaut, and the spaceship is orbiting. It's free falling around. That's the key. It's in free fall. It's weightless because it's in free fall. But there is gravity in space. All right. So the point is, gravity is one of our kinetic forces. Kinetics deals with forces. Gravity is the first one we need to consider. We always have to consider gravity because it's always here on planet Earth, from planet Earth. Okay? Then in biomechanics, we do a lot of forces dealing with pushes and pulls. Okay? Push forces are compartmentalized with compression. Pushing has a lot of compression to it. You think about if you push your hand on your desk, or you push on a bar. Let's say here on this dumbbell, right? I'm pushing on this dumbbell. So objects can influence other objects with pushes. And pushes deal with compressions. Objects are very, very strong in compression. That's the old, Easter's coming up, and that's the old, you take an egg and you try to compress it at the ends and it doesn't break, right? Objects are very, a lot stronger in compression than they are tension, being pulled apart. You can handle a heck of a lot more force being compressed. That's why it's a lot easier to do a lot of weight with pushing movements than pulling movements. The world record for the bench press is a heck of a lot more than any record of a pull. Should make sense, because when you're pushing things, you're compressing things together. Bones can push, remember, okay? The other end of that is tension, pull influences, pull forces, ropes. Now, you can get into the rabbit hole a little bit. Well, technically, whatever you hook the rope to, it's pushing on that end. But to apply that push, it's being pulled. So that's important. You remember in 310, we talked about how muscles can shorten or be lengthened. So tension is pull forces. And those kind of go hand in hand, where planet Earth, let's go back to the tricep push down exercise, right? Planet Earth is pulling on that weight stack. And then the attached cable is pulling through tension. This is physical pull. Gravity is let's say imaginary. It's not imaginary, but it's non-contact. In other words, the center of the planet is trying to influence your motion without actually touching you. Tension, there has to be connection, there has to be touching. So the cable is being pulled. There's tension in the cable. There's pull force in the cable. And then the cable attaches to a handle, and that handle is being pulled. But the actual connection to your hand and the handle is actually pushing. So again, these are kind of inside the rabbit hole concepts. The cable is being pulled, but the handle itself is pushing on your hands, and in reverse, your hand is pushing on the handle, okay? So in biomechanics, the main forces we are going to look at in terms of is gravity, pushes and pulls. Now, that's external. internal forces. You guys know this really, really well from 310 and 415. Muscles. Muscles, 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 muscles. And how do muscles work? Pull. Muscles can only pull. So muscles work with tension. Tense muscles. Think about that. You know, someone's got tense muscles. It's a spin-off of the concept of tension. So, intrinsic movement influencers, muscles. How do muscles work? Tension. Now, just like the cable, this will hopefully make some connections for you guys. Don't forget the secret word. Finished. Secret word from the secret camera. Just like on the tricep pushdown, this is cool. Gravity pulling on the plates, tension from the cable, compression from the handle. Remember, matter can't be created or destroyed. Energy can't be created or destroyed, but it can be converted. Let's apply that to muscles. Muscles pulling on bone. Bone pushing on other bones. Think about that for a second. When you're doing a bench press, right? Let's pretend I'm doing, chest press since I'm upright. Doing a chest press. Think about this for a second. My pecs, just going to use the pecs, but my horizontal adductors, pectoralis major being apart, pulling on my humerus in a direction of horizontal adduction. What is the humerus, the actual bone, doing? The humerus is pushing on my ulna. Think about that for a second. As my chest muscles pull on the humerus, that's why you get a nice little olecranon hook on there, because there's forces. If this is my humerus and this is my ulna, it's not perfect, but the point is that, and I'm taking away the olecranon, but the point is that when I'm doing this bone is pushing on that bone. It's kind of cool. Muscles pull. What are they pulling on? Bones. Bones can push. Bones can compress. Bones can transfer their influence through compression, push. That's super cool, man. So remember, muscles can pull, but they pull on bones. Bones can push. And again, that's why when you're doing pull things, you don't get the added advantage of bones contributing. When you do pull type things, the bones are actually being pulled apart. Like you're doing a pull type activity versus a push type activity or movement or exercise. That's cool. Pull things, push things. So again, that's kind of why you can squat the house, but you can't necessarily like hamstring curl the house. That's why you can bench the house, but you can't necessarily row the house. Row, row, row your house. So today's lecture emphasized kinetics, forces. The main forces we're going to look at in biomechanics: gravity, non-contact influence, and then pushes and pulls outside of your body and inside of your body. Okay? Tomorrow, or Monday's lecture, we're going to get into kinematics, movement variables. I'm going to do a lot of definitions for you guys. So make sure you jot that down. It's all in your book, but you're going to need to define. You're going to need to know what terms are for your exam, okay? Don't forget the keyword, the password for today's lecture. And guys, social distance, man, okay? Social distance. If you guys have any questions, text me, email me, we can FaceTime, we can Zoom both. We'll make it work, okay? Y'all have a good weekend.